So in the previous videos, we have seen on the introduction part of thermal comfort on aircrafts, we have seen the survey of literature which we have done. And so we've seen the range of temperature and relative humidity that is experienced on board short haul flights based on the questionnaires and a long stretch of surveys. And we've also seen the modeling and the mesh and the other computational aspects of this problem. Now we'll move on to the most interesting part, which is the results that we've obtained. So first of all, here is this. We got started with the velocity distribution. This is what we saw. As you can see, the air is coming in from the top half of from the top cabin inlets, and it is going out from the cabin's lower area near the passenger's feet. So it's near the passenger's feet and is near the passenger's head as well. So this is what we had. We had the distribution of the velocity. We had assumed different cabin temperatures. We assumed different cabin humidity as well. As we all know, we have taken 20, 22, and 25 as the temperatures, degrees Celsius as temperature of the cabin. We've taken three temperatures and we've taken four relative humidities: 15, 20, 25, and 30. So these are the, you can say 4 times 3. These are the 12 types of scenarios which we have considered. We've considered more scenarios as well. That will become clear as we move on. So first of all, but on this slide, you can see the velocity distribution in different parts of the cabin, which I've obtained from the simulation. Now we have taken the data from the CFD simulation on the value of the velocity at different points has been fed into our the model which we created for thermal comfort, and this is what we got from this. Oh yeah, and before we go there, this is what we use to actually. You may ask, how did you capture the data? This is how we captured it. We made two lines. As you can see here, there are two lines, two white lines, one near the foot and one near the head. So the white line near the head, it goes past the three sections of the seat: the window seat, the middle seat, and as well as the aisle seat. Okay, so and goes near the passenger head area and near the passenger's foot area. So these, so we have used this thing to capture the thermal comfort in all parts of the passenger, near the passenger's head and their foot. In this, when we are giving the results, will be focusing on data that came in from the head region of the passenger, because that is the head region. The torso region is the place that is more prone to changes in the thermal conditions and more prone to the passenger's comfort level on flights. So yes, and this is the Excel sheet which we use for actually obtaining the values of PMV and PPD. You can see here that there are various points. The various points are from these two lines. These two lines are set of points, and along these points, we have obtained the value of the velocity which we got in from the simulation, and we have also inputted the value of the air temperature in the cabin, which has been assumed to be uniform. So the cabin's temperature has been inputted. We also have to input the air relative humidity. All the inputs are given in yellow color, and we also have the passengers clothing level. The clothing level, as explained before, is a personal thermal comfort parameter. And there's also the metabolic rate. Metabolic rate has been taken to be equal to 70 watt per meter square, slightly more than 1 Met. This is what most passengers who are seated, human beings in seated position, produce this much heat, and the flux of this heat. This is how much we produce. There's one more very important parameter on the top, is the altitude. The altitude that the passengers will feel inside their cabin. Now, if the plane is flying at a very, very high altitude, at its cruise level, passengers will never feel the atmospheric air pressure that they'll feel on the ground. They actually feel slightly less, because the cabins, the aircraft systems of pressurization, no matter how much robust your system of pressurization is, there'll always be some amount of the pressure leaks, because the pressure outside the cabin will be very, very low. You much lower than the atmospheric pressure. So passengers will always feel a lower amount of pressure than what they would have actually felt if they were on the ground. And this will vary. For example, if you're at an altitude of, if you're at cruise level, you'll feel the altitude, you'll feel the pressure that a person would have felt if they were at a height of 5,000 feet. This is what you obtained from our literature surveys. 5,000 feet is what you have taken. It can be altered as well. As you can see from this Excel, we can very easily make changes and we can get different values. And of course, we have taken 2,000 feet for takeoff and cruise. So when the plane is taken off, when the plane is in cruise, we can get these values, because it will be at an intermediate altitude. And of course, we can also put 0 when the plane is on the ground level. Now, here are the two the parameters which you considered. The basic two ones are the clothing factor. You have taken a clothing factor of 0.7. You also taken clothing factor 0.8. So 0.7, 0.8 we have taken, so that we can see how it is varying with the clothing factor. Of course, passengers going on airplanes, on short haul flights, they're mostly they're mostly more than average amount of dressing they have. They wear a slightly higher amount of clothes. So that's why we've taken 0.7 and 0.8. And we considered three scenarios: ground, climb, and cruise. So ground, climb, and cruise for each of the clothing parameters we have taken. Here is our results. We have taken the results at multiple points. We have taken the results. Let me move this thing. So we have taken the results at, as you can see here, we have taken it at, you can see here both PPD and PMV. PPD is percentage of the people dissatisfied, and PMV is of course the predicted mean vote, which we have discussed this thing, how these two are varying. And here you can see altitude 0 feet, metabolic rate 1.2, which is around 70, and the clothing factor is kept at 0.7. This 0.7, if we've taken three scenarios, so this is one, the remaining two are this, at altitude of 2000 feet, which is takeoff or landing, and we have 5,000 feet, which is the cruise, which is actually the more crucial one, because the plane spends more time in this arena in the cruise mode. So these three are for the clothing level of 0.7, and the remaining three are for 0.8. Now, so we will now use, so based on what we're getting from this data, we have drawn some conclusions which can be very useful for engineers of the future when they're designing an efficient environmental control system. And so just keep in mind, as we go on to the conclusions, we have taken 4 different values of relative humidity: 15, 20, 25, and 30%, and 3 different temperatures: 20, 22, and 25. Now, here are the conclusions which you got. The graphs of PPT, predicted percentage dissatisfied, indicate that 25 degrees Celsius is the most comfortable cabin temperature, which of course it's obvious. Like for most human beings, 25 degrees Celsius is the most ideal. Because at 20 or 22, we tend to feel a bit cold. We tend to feel colder. This of course varies from person to person. For example, a person from Siberia might not feel as cold as 20 degrees as a person from India might, because they're both grown up in different uh, environments. But at the end of the day, they both feel cold. So 25 degrees Celsius is mostly accepted as the comfortable temperature. And here's one more thing which we found: in these temperature ranges, in all the range of temperatures, passengers tend to feel warmer as the relative humidity increases. So if we have a higher amount of moisture, passengers tend to feel warmer. And one more very important thing is, if you keep the temperature and the humidity constant, then as the aircraft begins to ascend and as the pressure inside the cabin begins to drop slightly, passengers tend to feel colder. This we got from the PMV values. So passengers tend to feel colder as the aircraft ascends. And these 2 points are very crucial points which can help engineers design the ECS of the future. Okay, for lower temperatures in the range of about 20 degrees Celsius, 20 to 22 degrees Celsius, if you look at relative humidity, what relative humidity should you be having? 30% as given the most comfortable environment on board. Now, it's already been clear that passengers feel colder at 20 degrees Celsius, because that's a very cold, it's a relatively colder temperature. And also passengers tend to feel warm as you increase the relative humidity. So when your aircraft is in cruise mode, temperature will invariably drop a little bit. Okay, so it will be more in the range of 20 to 22 degrees Celsius. In those areas, it is absolutely essential that you maintain the relative humidity of 30% to give the most comfortable environment on board, because passengers will feel colder. But if you maintain the moisture level if you maintain the moisture at a higher level, then passengers will try to make the passengers feel warmer. So if you keep the PPD lower and you keep the PMV at a more comfortable range, so passengers will feel more comfortable in this. Conversely, the temperature is very high at 25 degrees Celsius. The exact opposite happens. The passengers will feel more comfortable at lower values of 15%. You see, if you increase the temperature, passengers will feel warmer. If you increase the RH, passengers will again feel warmer. but we see there's a reversal between these two weighing factors as you move within the ranges of temperature and humidity which passengers feel on board aircrafts. At a higher temperatures, for example, when the plane is on the ground, the when the plane is on the ground, the higher the temperatures are invariably higher, because of course if you're in a hot airport, temperatures will be higher. In these places, maintaining a slightly lower value of RH will keep the passengers more comfortable, but as the plane takes off and climbs, the temperature will invariably drop, and also passengers will feel colder. For that reason, temperature will invariably drop. They'll also feel cold because the aircraft is ascending. As mentioned before, as we've seen from our results, passengers will feel colder as the aircraft ascends. So these two weighing factors will make the passengers feel cold. So you have to put in extra effort to maintain the humidity level in the aircraft's environment that will keep the passengers comfortable and make them feel warmer. So these are the conclusions which we've derived from this thing. At high altitudes, where cabin temperature is lower, maintaining optimum RH is very crucial for passenger comfort. Conversely, if cabin temperature is higher, the, the we have to keep the RH at a lower value. But we can also see one more very important, very interesting thing: the effect that the humidity has on thermal comfort is very low. Is very low at higher temperatures. So the ECS system need not work as hard to maintain an optimum relative humidity when the plane's on the ground. So when the plane's on the ground, there's of course going to be humidity coming in from the atmosphere. So there's literally, in that way, someone can argue that there's no need to actually for the aircrafts to actually maintain, to actually push the ECS to maintain a system on board. But when the doors are closed and let's say the aircraft is taxiing, and if you are in a very busy airport like New York's JFK or Los Angeles airport, then the taxiing itself could take a huge amount of time. So in that time, the plane is on the tarmac and it's relatively hot inside the cabin. The effect that the humidity will have on thermal comfort is very less, very negligible. This has been obtained from, this can be verified from our PPD graphs. Um, so these are some of the recommendations which this small study has found, that engineers who design the future ECS systems can keep in mind. Now, coming to the limitations. First of all, we said that the mean radiant temperature we have taken exactly equal to the cabin temperature. This definitely is not true. We are talking about the limitations of this model, and we'll also go on how this model can be expanded. Coming to the limitations, as I said before, mean radiant temperature has been taken equal to the relative to the actual air temperature in the cabin. Now, this is because we have assumed the aircraft to be an absolute adiabatic closed system in which there's no heat exchange with the outside. This is pretty obvious. It's not true, because especially when you're flying in daytime, there can of course be radiation coming in from the window. You can also have radiation falling onto the aircraft and the aircraft's external body heating up, and that heat actually being conducted into the aircraft's inner skin and then being conducted inside. You can also have heat being generated on the outside because of the skin friction of the high speed air molecules with the aircraft. This also heat up the external aircraft. So this will result in some temperature, or you can say a cooling load on the aircraft due to the external conditions. So in this study, we have assumed that the we've assumed that there's no heat load due to the external factors, which is of course not true. But this study can definitely be expanded to include that as well. And of course, we have taken a very simplified model of an Airbus A320. We have taken into account only one row of seats. We also have not taken in human mannequins. We have instead simply put in the seats, and we have taken the seats to be approximating the humans. So this is also one limitation. And we've also assumed uniform distribution of temperature. This is not a very big problem, because from what we have seen in aircrafts, the temperature variation across the cabin is not very high, especially in a steady state scenario. Also, it's been recommended by ASHRAE that the temperature difference between different points in aircraft should be kept as low as possible, so as to ensure a thermally comfort environment for the passengers. So, however, this is still a limitation, because it will not 100% be uniform everywhere. And of course, the range that we have assumed is, it can be considered narrow because we've only taken 20, 22, and 25 degrees Celsius, and we've only taken 4 values of relative humidity. We can even expand this thing into an optimization type of uh, a project in which we actually optimize and find what are the perfect conditions of passenger comfort. So these are the limitations, and coming on the applications. Also, one small note: every time I mention a limitation, we actually have plans to overcome the limitation and expand this model in the future, so that we can make a more holistic and a more complete model. Coming to applications, of course, this is very, very important in long haul flights. If you take the 19-hour flight from New York to Singapore on Singapore Airlines, then you need to have a very efficient and a robust ECS to keep the cabin temperatures as comfortable as possible for the passengers. And so that is the goal of this project. It is create a model in which all the parameters that go into defining thermal comfort can be bought under one roof, and from there engineers can experiment, and they can change and experiment and come up with the best possible ECS system for one particular application as well. So this is very important for long haul flights. Even though in this study we will only consider short haul flights, this is extremely important for long haul flights. But it's even more important for long haul flights, in fact. And of course, the cabin layouts. This study can be used by engineers who are designing the aircrafts of the next generation to experiment with different cabin layouts, different cabin air distribution system, with different cabin ventilation systems, like the mixed ventilation cabin, the displacement to ventilation. These are all different things which can be explored. So this is the utility of CFD coming into simulating the thermal and general passenger comfort inside aircrafts. So I hope this the presentation as we have been able to convey something useful to viewers. And so yeah, we hope that we have shown you to what level these CFD can be used for this. And I also like to mention that this project was done as a collaboration between with me and Chaktab Nishant Rana Sahib, who's unfortunately not present at this time with us for the presentation. But I have to mention his name also. He's also so this project was possible. It happened because of his efforts as well. He was also very, very helpful and very much determined in making this project a success. So this is what we have from us. So thank you for your attention and for watching. And if you have any questions, you can to get back to us, to me or Nishant, and we can definitely take up further discussions on this project. Thank you.
Thank you, Prithvi. You were great. I think I should mention that Prithvi is very good with aerodynamics and airplanes, and he's been working on projects related to airplanes and small size modelings of airplanes and practical manufacturing of airplanes on our campus. And if you have any queries, you can definitely comment, and Prithvi or Nishant will be very much glad to help you out. Thank you, everyone.